So another aspect of reaction rates is talking about the half-life. So how long is a piece of string, sort of thing. So how long does a reaction take? Well, you can't really talk about how long a reaction takes because of the exponential dependence on the concentration with time. So if you have A is disappearing as a function of time t, since it's nonlinear, it doesn't really make sense to give this absolute t value. And that's why we talk about half-lives. How long does it take to reduce by 50% of your initial conditions or your initial concentrations? So that way you have a normalized way to compare reaction 1, reaction 2, and so on. Okay, so how do we find the half-life? Well, we know that our first, so this is for first order. Because spoiler alert, the half-life is different for every type of reaction, or every type of order reaction. So for first order, you would take your integrated rate law and you would set up the conditions so that, you know, at t equals 0, the concentration of A is equal to the initial concentration. And at the half-life, when t is equal to t1/2, A is equal to A0 over 2. Okay, so you plug these in, and then you determine and solve for what t1/2 would be. So let's go ahead and do that. So if I have log of A0 over 2, oops, is equal to minus k t1/2 plus log of A0. Oh my gosh, that's really hard to. So now what we're going to do is we're going to say log of A0 divided by 2 minus log of A0 is equal to k, minus k t1/2. I can combine these two, which gives me log quantity A0 divided by 2. A0 is equal to minus k t1/2. And so then I could say, well, that's just A0 and A0 cancel. And I'm left with minus log of 2 divided by k is equal to t1/2. Sweet. Well, that was easy. So actually, I think, hang on. Go team. Sorry, I got confused by this negative sign that I was like, wait a minute, there shouldn't be a negative sign. I see my mistake. I've got log of 1 over 2 divided by minus k, but this log of 1 over 2 is the same as log of 2, or a minus log of 2. And so then I say minus k, that cancels, equals t1/2, which I'm left with log of 2 divided by k. Sorry about that, equals t1/2. Hopefully you're following along and being like, Allison, you have a negative sign that makes no sense. It's about you paying attention. Okay, cool. So anything interesting about this half-life relationship between K and half-life? Notice what's missing. The initial concentration. So the half-life for a first order reaction has nothing to do with the concentrations that you're starting with. It's independent of concentration. Not true for other reactions. So for second order, you have t1/2 equals, let me grab it, 1 over k times the concentration of A0. So the half-life for a second order is dependent on the initial conditions that you have, whereas first order is not dependent. The uniqueness of the different types of ordered reactions and the way that their kinetics moves forward is challenging because you have to make sure you're taking everything into account when you're describing your system. Cool? So if you check over into table 17B.3, the one I showed you earlier, you can see the listing of the half-lives and kind of the generic formula that you can use to identify what the half-lives are. Okay, I think that's all I want to talk about here. Go team. And you can do the same approach of finding half-lives for the other orders of reactions. And once you have a half-life, then you can start to look at, using these functions to then get quantitative information from your systems. Go team.